In 1572, Danish astronomer Tycho Brahe noticed a completely new star appear in the night sky that was brighter than any other object in the sky. This new star was evidence of a changing heaven, which contradicted the church doctrine at the time. Without knowing it, Tycho had discovered a supernova. This discovery prompted King Frederick II of Denmark to build Tycho an observatory where he could follow the motions of the wandering stars and other celestial objects. Even though Tycho carried out his measurements with impressive precision, he still wasn't able to find any clear evidence of Earth's motion through the heavens. So, until the end of his life, Tycho remained a geocentrist, holding the popular view of the time that all other objects orbited the Earth. After Tycho's death, German mathematician and heliocentrist Johannes Kepler inherited all the data Tycho had accumulated over the years. Kepler's goal was to find a geometrical model of the universe that matched the best observation of the time. The dots on the orbit represent the planet's position at equal time intervals. Although Kepler hypothesized circular orbits, some data points differed significantly from the circular path. Instead of assuming that Tycho wasn't as precise as he thought he was, Kepler rejected the notion of a circular path and adopted an elliptical orbit. Additionally, the Sun was not at the center but located at one focus of the ellipse. These findings are summarized in Kepler's first law of planetary motion. A planet orbits the Sun in an ellipse, with the Sun at one focus of the ellipse. Kepler didn't stop there. He discovered more insightful details about the motion of the planets. The planets' positions are not equally spaced over time. They are spaced in a specific way. The area swept by the position vector of the planets between some moment of time t and some future moment t plus delta t is the same as the area swept between t prime and t prime plus delta t, which means in the same time interval since delta t is the same in both cases. This may not sound interesting at first, but it implies that the planet's speed changes in a very precise and predictable manner. When a planet is closer to the Sun, it moves faster, and as it moves away, its speed decreases. These findings are summarized in Kepler's second law, which states simply, a line connecting a planet to the Sun sweeps out equal areas in equal time intervals. Kepler's third law was published later in his book, The Harmony of the World. In this law, Kepler concluded that there is an exact relationship between a planet's average distance from the Sun and its period of motion. The planets do not orbit the Sun at the same rate. As you move further from the Sun, objects take more time to complete an orbit. The relationship between the period of motion and the mean distance from the Sun can be described mathematically as t squared equals a cubed. This is Kepler's third law, where t is the orbital period of the planet measured in years, and a is the average distance from the Sun. To recap, we've had a high-level overview of Kepler's laws. In one of the next videos, we'll dive deeper into describing the geometry of ellipses. Finally, I want to thank my patrons, Jessica and Sergey Misuk, sorry if I butchered your name, for their kind support on Patreon. If you want to fund future videos and learn how to make these animations, check out patreon.com/explainstuff. Thank you for watching.